Hello, dear students, and welcome to today's tutorial in which we are looking at functions. We are going to look at these functions from the following perspectives. We will study the function from the function itself. We will study the function from a given table of variation, and we will end up studying a function from its graph that has been given. Please make sure you watch this video to the end, and don't forget to share and leave your comments below. Let's begin with the first. First of all, we are given this function x squared minus 4x plus 3, and we have to study this function. Whenever you ask to study a function or to sketch a curve of a function, you know about the elements that are involved. You have to look at the domain of definition, the limits of the boundaries, the asymptotes, the intercepts. You draw up the variation table after looking at the gradient function, and you end up sketching the curve. There are other parameters like center and axis of symmetry, which we're going to visit in this topic and in other topics. So the first thing here is domain of definition. And knowing that this is a quadratic function, we know that quadratic functions are defined with the set of all real numbers. So the domain here is from negative infinity to positive infinity, or the set of all real numbers. However, I like this notation in intervals, which makes me to see the different bounds that are involved. The next thing is to get the limits to the bounds of the domain. And as you've been taught limits for quadratic functions, we can just approximate by taking their term with the highest degree. In this case, x squared. If you had minus 2x squared, that is what you're going to use, minus 2x squared or plus 5x squared, whatever. But it's approximately equal to x squared, or the term in x squared, as x tends to infinity. Why? Because these other values or these other terms will have negligible effect on that value. So we just have minus infinity. When you square, that's going to give us positive infinity. And equally, the limit as x tends to positive infinity will just be positive infinity squared, which still gives us positive infinity. Normally, looking at this curve, you can equally see that the coefficient of x squared is plus or is positive, which therefore means that this curve has a minimum turning point. And it is clear from the limits that at negative infinity, it is positive, and at positive infinity, is both positive. We are going to see that on the curve. Quadratic functions of this type, note I specify of this type, normally do not have asymptotes. However, exponential quadratics at times have asymptotes. Most quadratic exponential quadratics will have asymptotes, horizontal and yeah. Now look at the intercepts. The intercepts are the points where the curve cuts the ordinate axis. So when x is equal to 0, we look for the corresponding value of y. So f of 0 will give us 3. So when x is 0, the y value is 3. Now what happens when y is 0 instead? At y equals 0, we just equate this quadratic to 0 and solve for x. You can solve this quadratic, and when you solve, the values you're going to have 1 and 3. Those are going to be the roots of this quadratic. You now look for the value of y when x is 1. Normally, you will not have to stress to do that because you have just said when y is 0, these are the corresponding x values. So the intercepts here are 1, 0 when x is 1, y is 0, and when x is 3, y is 0. So we have 3 intercepts, and throughout this tutorial, I will be using A, B, and C, and so on for the intercepts, and whenever I have asymptotes, I will use x, y, z, and so on. A, B, and C for intercepts, and x, y, and z for turning points, okay? After having this, next thing to look at is the gradient function, or call it y dx, call it whatever, but that's the gradient function. And the derivative here is going to give us, the derivative of x squared is 2x, and the derivative of minus 4 is minus 4x is minus 4. The derivative of 3 is 0. So you can see all of these derivatives here. And then we solve the equation dy dx equals 0 at the turning point, right? When you solve that dy dx equals 0, you're going to have 2x minus 4 equals 0, and that is going to give us x to be equal to 2. Our turning point consists of an x and a y value. We know that at the turning point, x is 2. So what's going to be the y value at the turning point? So we look for f of 2, and f of 2 is going to give us -1. Therefore, the turning point at x is 2, -1. Those are the coordinates of the turning point. And note, for quadratics, the turning points can equally give us additional information. The point or the line x equals 2, looking at the turning point, x equals 2 is the axis of symmetry. This is the line that divides the quadratic into two equal parts such that there are mirror images. And the value of y equals -1 is the minimum value of this quadratic, the smallest value that this curve, or the smallest value of y on this curve. There is no other value smaller than -1. So we call this the minimum value of y. We can now sketch a variation table. And this variation table consists of the first row. We start by looking at the domain of definition. On the domain of definition, we have from -infinity to +infinity. Yes, there is a turning point. A turning point occurs when x equals 2. So only the x values occur here. As you can see, this is x. We have the domain from -infinity to +infinity. And there is an x value in between those values. That is x equals 2, which occurs the turning point. In rational functions, that is in the next video, where we are going to be having vertical asymptotes, we are going to include the vertical x values here of those vertical asymptotes, as you can see. Here we have just a turning point, so this is okay. The next thing now is the gradient function. Here we are interested in knowing how this curve behaves in these various regions. That is from -infinity to 2 and from 2 to +infinity. We want to know if the curve is increasing or decreasing. So with this gradient function, we are going to be using signs. Negative will stand for decreasing and positive for increasing. Note that the variation table is some sort of sketchy representation of the curve. We want to see how the curve will look like when it is sketched. So f prime, we are going to be getting using either negative to show that the curve is decreasing or positive to show that it's increasing. And we are going to substitute any value between -infinity and 2 between in this region. But since this is a turning point, I'm going to use broken lines here. Okay. So from -infinity to 2, we can use 0, for example, in this gradient function. If we substitute 2 here, we are going to have 2 times 0 minus 4. That gives us a negative number. This therefore means that in this region of the x from -infinity to 2, the curve is decreasing. And note that at the turning point here, the value of f prime is 0, okay? At the turning point, the value of f prime is 0, because if you put 2, if you like, you fit 2 into this gradient function, you're going to have 2 times 2, which is 4 minus 4, 0. At the turning point, f prime of x is 0. Now, in the region above 2 to +infinity, we can get free and test in this gradient function. We will have 2 times 3 is 6 minus 4, which is 2. That number is positive, telling us that this function is increasing. Now we've completed the region where we have to discuss about the gradient function. Now let us move to the function, the curve itself. Here we've been told that it is decreasing. So we are going to put a line to indicate that it's decreasing. This line indicates that it is decreasing. This is negative. This line always begins from left to right. It is decreasing, so it decreases from left to right. And equally on the right-hand side of this interrupted line, the curve is increasing, as you can see. So it's increasing. This positive sign tells us it is increasing. And everything begins from left to right, so it increases from this left to right. Now, how do we get the values? Because it cannot just decrease from nothing to nothing or increase from nothing to nothing. It has to increase from something to something. Now, whenever you have positive infinity on your curve, positive infinity must always be at the up position. Whenever you have positive infinity, it must be up. And whenever you have negative infinity, it must be down. The highest value that a curve can take is positive infinity. So a curve cannot increase from positive infinity to another value because positive infinity is the highest value. From positive infinity, a curve will only decrease. It cannot increase because positive infinity is the highest value that the curve can take, although it's not actually a valid description of the highest value. So whenever I have positive infinity, these are the mistakes that students make, technical students in particular, and most of the grammar students who really don't, we're just trying to have hold of this variation table stuff. So a curve, whenever you have positive infinity, and these values are coming from limits. How did I get this positive infinity? So as x tends to negative infinity, look at it very well, we get this from the limits. As x was tending to negative infinity, The limit of f of x as x tends to negative infinity gave us positive infinity. And here, when x was equal to 2, we saw that this is at the turning point, right? At the turning point, the value of y is -1. That is why we have -1 here. And as x turns to positive infinity, we equally solve this from the limits. Y also turns to positive infinity. That is why we have this value here. What other thing we have to remark is that x equals to is the axis of symmetry. I made mention of this, and therefore, looking at this curve also, this curve is like a U. This curve has a minimum turning point. And as I said before, from the equation of x squared in this quadratic equation, which is positive, you know that this curve has a minimum turning point, okay? You can now sketch this curve, and that's not going to be a big deal. So this is a coordinate axis, and we have intercepts at 0, 3. We have another intercept at 1, 0, and another, we have a turning point rather at 2, -1. This is a turning point, and this turning point, you have this double directional arrow. We equally have another turning point at 3, 0. So these are the 3 intercepts that we have and 1 turning point. We now use a smooth curve and link all of these points, and this is what we have. For those who've done general education and even grammar, let me see, general education, sorry, and technical, they must have been sketching these quadratic curves by taking values of x, maybe they say from -1 to 5 and so on, and it's the same stuff. So if you sketch this curve using that same procedure, you are going to have this same. But at advanced level, they would like you to give the domain of definition, the limits of the bounds, the asymptotes, the intercepts, the gradient function, the variation table, and before you sketch the curve. Okay, this brings us to the second question. But before that, let us look at some remarks. So the intercepts here, the x-intercepts will give us the root of this quadratic, and these are the x-intercepts at x equals 1 and x equals 3. This gives us the root of this quadratic. And equally from here, if you have to get this axis of symmetry, this is the axis of symmetry, which divides the curve into 2 equal parts. You consider this, it is this line like this. This line is the axis of symmetry. And to get the axis of symmetry from quadratics, you just take the average of the roots. The roots here are 1 and 3. Average of 1 and 3 is 2, right? And you can equally start from the turning point. That's 2, x equals 2 is the axis of symmetry. From the average of roots, you can equally get the axis of symmetry if the curve is a quadratic curve, not an exponential or logarithmic quadratic, a simple quadratic. And equally, we can get the abscissa. The abscissa refers to the x-axis. At times, students fail questions because they don't know the meaning of abscissa and ordinate. Abscissa just means the x-axis, and ordinate means the y-axis. Take note of this. Abscissa, A comes before O, X comes before Y. So abscissa, X, ordinate, Y. Okay, don't forget. If you forget, just say that A comes before O and X comes before Y. So first, last. This brings us to the second question on quadratics. Please stay tuned. The second question that we have here. All right, let's take it. Guys, please don't forget to subscribe to this channel and share this video with your friends and leave your comments. We upload videos almost every week, and you can join us as well. And we equally have a partner program that we are working with that strictly prepares students for the GCE. It's called the GPP. You can register into the GPP program directly by registering through the GCE Math Panel. We are one of the affiliates, and they strictly focus on exam answering skills for 20 years. For the past 20 years, every year, registrations always begin by August, and they prepare you in 6 to 9 months, not just in mathematics, but in physics, chemistry, biology, and all the subjects. So you can just go to their website, www.gpp.blogspot.com, and you get additional information, or you can contact us as well. Now, looking at the second function, which is also a quadratic, as I've said, for simple quadratics like this, in which all the terms are in x, the domain of definition does not change. It's just from negative infinity to positive infinity, or the set of all real numbers. Now, the second thing we are going to look at are the limits. And for quadratic, the limits, we just approximate by taking the term with the highest degree. In this case, we have minus 2x, and we're going to substitute the values of positive and negative infinity is this at these boundaries that we have. So the limit as x tends to negative infinity will be negative 2 into negative infinity squared. So this limit is negative infinity, and the limit as x tends to positive infinity is negative 2 into positive infinity all squared, which is negative infinity. Note that for quadratic, the limit at positive infinity and negative infinity must always be the same for simple quadratics like this. So if the first limit is positive, the other one must be positive. If your two limits have opposite signs, then you have a problem. Okay. Now, there are no asymptotes to quadratics as we mentioned earlier. That is for simple quadratics. Exponential and logarithmic quadratics will normally have horizontal asymptotes or vertical. We are going to see that in subsequent lessons. For the intercepts here, when x equals 0, the value of y will be 3. So we have the first intercept at a is 0, 3. And another intercept, what happens when y equals 0? So when y equals 0 and we solve this equation, the values of x will be, we have minus 1 and plus 1.5. So therefore, it means that the other two intercepts we have are minus 1, 0, because this is minus 1, y is already equal to 0, and 1.5, 0. So we have 3 intercepts for this particular curve. We now move on to our gradient function. When you differentiate this function, you bring down the power, that is 2, multiplied by minus 2, that's going to give us minus 4x plus 1. Differentiate 3, you have 0. So this is the derivative that is here. To get the value of y at the turning points, we solve this equation, minus 4x plus 1 equals 0. And that gives us the value of x to be equal to 0.25. We have to look for the corresponding value of y when x equals 0.25. That will give us 3.125, right? So there is a turning point at 0.25 and 3.125. We now move to our variation table. So for this variation table, the domain is from negative infinity to positive infinity. These values must come from the domain. If there was no negative infinity here, I will not put. Does not mean that all the time it's from negative infinity to positive infinity. Do not study by rote. Do not do rote learning or cram work. Cram work will not help you. Try to understand these principles. And equally, there's a turning point at 0.25. You can see this turning point at 0.25. It's included here. That's the x value at the turning point. Now, since it's a turning point, I'm going to include a line here to indicate that it's a turning point, a broken line. The curve actually passes here. Now, of the gradient function between negative infinity and 0.25, you want to test the sign if the function is increasing or decreasing. Take any number and use any x value between negative infinity and positive at 0.25. 0 is always very sweet. You can take negative 1 as well. It doesn't matter what you take. You are going to have positive here. For example, if you put 0, it will be positive. Put negative 1, it will still be positive. Negative 4 times negative 1 is plus 4 plus 1, 5. So in this region, the function is increasing and be above 0.25 from positive infinity. We can take 3, minus 4 times 3 minus 12 plus 1 minus 11. So it's decreasing in this interval. At the point where x equals 0.25, the gradient function is 0. Above, it is decreasing. So this curve is increasing, and on this interval, it's decreasing. So when x tends to negative infinity, y tends to negative infinity. Negative infinity must always be at the bottom. As I'm telling you, negative infinity must always be at the bottom. So don't be confused. Where should I put the negative infinity? It's at the bottom. The position of negative infinity is always down. Position of positive infinity is always up. So this function is increasing because the smallest value a curve can take is negative infinity, if the curve actually moves from negative infinity. So this curve is increasing from negative infinity to a particular value. Now, when x tends to positive infinity, the curve is still negative infinity. So negative infinity must be down here, as you can see. And when x is 0.25, the value of a y is 3.125. You can see that from the turning point, okay? So this curve now increases from negative infinity to 3.125 and decreases from 3.125, which is the turning point, to negative infinity. So remarks, x equals 0.25 here is the axis of symmetry, and the minimum value of y is 3.125. This curve is having a maximum turning point. How can you also prove this? Because the gradient function is positive before for values less than of x less than 0.25, and the gradient function is negative. So the gradient function changes from positive to negative. That only happens for a maximum turning point. As you can see, it's increasing. Then at the turning point is 0, and then it starts decreasing. That is for a maximum turning point. We can now sketch a curve. Our intercepts are 0, 3, minus 1, 0, and 1.50. We equally have a turning point at 0.25, 3.125. That is it. And these are 3 intercepts. You can link all of these points, and this is what we have. My curve might not be very beautiful, but that is what we have. Okay. So other remarks for this curve: the x-intercepts are the roots of the quadratic. The axis of symmetry we have already seen, and from the curve, x equals 0.25 is the axis of symmetry, while y equals 3.125 is the maxi value, the maximum value of y. Now, for these two functions, we have started with the function itself and moved to the curve. In the next question, we are either going to work from the table and look for the function, or we work from the curve and look for the function. Those are the two sweet parts of this study now. So that brings us to question 3. Don't forget to subscribe and share this video. This is property of the GCE Math panel. If you find a content somewhere else, make sure that you involve or explain it to us. Equally, this content can only be found again on Math 24 Super Channel, Math 24 Super Channel, or the GCE Math panel. Now, this is a beautiful question that's been given to us. We are given this variation table, and we are asked to study the curve of this quadratic function. We are also being told, given additional information, that the curve has an intercept at 0, 2. So we have to study this curve. We start by looking at the limits. Since this is a quadratic curve, you can see that as x tends to negative infinity. Okay, the domain of definition is already here. So from negative infinity to positive infinity, you can see this is the domain of definition, and 1.5 is a turning point. So since a quadratic, the domain is from negative infinity to positive infinity. The limit as x tends to negative infinity is positive infinity. And the limit as x tends to positive infinity, this is it, is positive infinity. These are our limits. This one is very easy. Now we have been told that one of the intercepts is at 0, 2. And since it's a quadratic, there is no asymptote. There is no asymptote. There is a turning point at this place, a turning point here. You have a turning point at 1.5 and negative 0.25. This is the turning points that we have from this curve. You can see it from here. Now the next thing, so let f of x, since a quadratic, let this be equal to this general form. We know the general form of quadratic is ax squared plus bx plus c. So let our f of x be equal to that ax squared plus bx plus c. From here, we know that we want to solve for a, b, and c. We have been told that f of 0 is 2. This is an intercept. F of 0 is 2. So we substitute this into this equation. F of 0 is 2. It means a into 0 squared plus b into 0 plus c should be equal to 2. And from here, we see that we already have the value of c to be 2. So we have the value of c to be 2. So how do we then get the other values? Now, the next thing we're going to do is, we know that the axis of symmetry is always given by negative b on 2a. Axis of symmetry is negative b on 2a. Right? If you want to, or you don't understand this, you can actually look for f prime. If you also look for f prime, differentiate this function, we are going to have f prime to be equal to 2ax plus b. And at the turning point, when we equate 2ax plus b, all right, let me just do it here. So we are going to have 2ax. When we differentiate this, we are going to have 2ax plus b. So we have 2ax plus b. When we differentiate this, our general form that we have. And at turning points, this is equal to 0, right? So from here, what will be the value of x? This x, which is we know that is the axis of symmetry because the x value at the turning point is equal to the axis of symmetry. From here, x will be equal to negative b on what? On 2a. So that is why we are talking about this. At the axis of symmetry, x is equal to negative b on 2a. And this axis of symmetry, we can see clearly from the domain of definition or from the variation table that it is 1.5. So it is equal to 1.5. So from here, we know that x equals negative b on 2a is equal to 1.5. So this gives us, this implies negative b on 2a is equal to 1.5. And from here, b will be equal to negative 3a. Because 2 times 1.5 is 3 times a, 3a. Now, this negative can move to the right-hand side. So from here, we have b to be equal to minus 3a. If we substitute these values of b and c in the equation, we'll have f of x to be equal to ax squared plus now our b becomes minus 3a, so minus 3ax plus 2. So the last thing we have to look for here is the value of a. Now we also know that at the turning point, f of 1.5 is equal to negative 0.25. F of 1.5 is equal to negative 0.25. So we substitute this in this function, we are going to have 2.25a, that is 1.5 square, which is 2.25 times a, minus 3 times 1.5 minus 4.5a plus 2. That should be equal to this value of 0.25. When we solve a here, it is going to give us 1. And since we know that b is equal to minus 3a, our b will be equal to minus 3. So our b will be equal to minus 3. Therefore, we have obtained this quadratic. So here you see how what we can do to come out with the function from the variation table. If you do not understand a certain concepts here, please you watch this video again. So the first thing to do is we use the intercept that we have been given, f of 0 equals 2. When we do that, we are going to have this value of c. Then we know that the axis of symmetry, or we can differentiate this, and then at turning points we equate to 0. And when we will have negative b on 2a, that negative b on 2a is equal to the x value at the turning point, which is 1.5. From there, we can get the relationship between b and a. We substitute that in the function here, as well as the c value. So the function is now in terms of a. But at the turning point, we know that f of 1.5 is negative 0.25. We substitute this and we have the values of a, b, and c at the end. So this is our function. Can we now sketch the curve? Of course, we can sketch the curve. So equally with the intercepts, or from what we have here now, because we knew only one of the intercepts, 0, 2. So from this curve that with this function we now have, we can now get the other intercepts. When y is equal to 0, as you can see, we solve x, we are going to have these other two intercepts, 1, 0, and 2, 0. Because at times in the exam, we may be asked to look for the function. Maybe asked to look for the function. So we can now beautifully sketch this curve. These are the intercepts. We have 0, 2. We equally have a 1, 0. We have a turning point at 1.5 minus 0.25. And we have another intercept here at 2, 0. Now link all of these points, and that is our curve. Okay. Okay. So now the last one, we are going to now work with the curve itself to get the function. We are going to study the function from the curve, and after that we'll move to rational functions. We will do the same principles we have applied here. We study the curve from the function, and we study the function from the curve. So we're going to work forwards and backwards, backwards and forwards. So the last question in this particular video is this question number 4. Don't forget to subscribe and leave your comments, your likes, and so on. So we are being given this function, and we are being asked to study the domain, the limits, and the intercepts, the roots, the turning points, study the variation table, the equation of the curve, the maximum and minimum values. So we start by stating the domain of definition. What's the domain of definition? This is a quadratic function. We already know the domain of definition. So we have from negative infinity to positive infinity. The limit now, the bounds of this domain of definition. You can see that the curve is moving to positive infinity and positive infinity. So the limit as x tends to negative infinity to positive infinity, you can start this moving up. And as x tends to positive infinity, we still have positive infinity, still upwards. The intercepts now, the intercepts are clearly here. We have x is -1, y is 0, x is 2, y is 0, and x is 0, y is -2. So these are the three intercepts which are there. B is still the roots and the turning points. For these roots, when x is equal to 0, we have, when y is equal to 0, we have -1. So when y is equal to 0, we consider these are the intercepts of x here. That is -1 and 2. And this gives us the roots of this equation. And we have a turning point here when x is equal to, since this is 1, so this should be normally a half. When x is 0.5 and y is equal to -2.5, all right, -2.25 rather, yeah. So here it's supposed to be -2.25, not -2.5, -2.25. Okay, -2.25. Then C, to study the variation table. So variation table, we know that the domain is from negative infinity to positive infinity. We have a turning point at x equals 0.5. So we include this line. From here, we see that before this turning point, the curve is decreasing, it's coming down. So the value of f prime here is going to be negative. At this turning point, we have 0, because at turning point, f prime is 0. And then above these turning points, the curve is increasing. So it's positive here. So this curve decreases from in this interval, and here it increases. So it decreases from what value? When x is negative infinity, y is positive infinity, you can see that we saw that from limits. At the turning point, y is -2.25 and moves to positive infinity. Note, this is -2.25. Let me indicate it again. All right, -2.25. And the next thing now is D, to state the equations of the curve. From here, this one is very easy because I can state the equation of this curve directly by using the roots. The roots are -1 and 2. And how do I form an equation from the roots? You can use x squared minus sum of roots plus product, or you can use the factorized form. You have x minus -1, which is the first root, x minus the first root times x minus the second root. So we have x minus -1 times x minus 2. And when we expand, we will have x squared minus x minus 2. So that's the equation of this curve. And what is the axis of symmetry? Axis of symmetry is the x value of the turning point, which is 0.5. And the minimum value of y is -2.25. Again, -2.25. So the curve is easier to study with quadratic from the curve itself, compared to variation table, as you can see. All right, so you can equally use x squared minus sum of roots plus products here, as we have mentioned. So thank you so much, and the next video is going to be on rational functions. We are going to apply all of these concepts there as well, and that's it.